All right, welcome to my talks, Just Switch the Compiler. My name is Arne. I work at Suka Engineering, which is a contractor company. So I have been working mostly in embedded projects in the last 10 years, a bit over 10 years. I've been working with C++ for quite longer. And I'm on the side a trainer for C++, for clean code and similar things. What I will be going to talk about is reasons why we would like to or want to switch the compiler, the steps involved, because it's usually not like flipping a switch, and pitfalls that we can expect. So this will be more or less a collection of war stories or experiences from all these past projects, and some strategies to avoid those pitfalls. Many in hindsight, some proven. Before we start, let's see a quick show of hands. Who in here is currently using more than one compiler on the same project in parallel? Almost everyone. So you probably know most of this. On the other hand, if you're using just one compiler, so other way around, who's using only one compiler? Two hands. Who of you have switched from one compiler to another in the past? Also a few hands. So let's start. Why would we want to switch? I mean, being at a C++ conference, you probably are listening to lots of talks about the shiny, nice new things in C++ 23, 26. And you come home and say, well, I want to use these. And you say, well, but my compiler is old. I'm using C++ 17, some projects maybe 11, 14. So I want to switch to a newer compiler to use these features. This is one reason. Other reasons, especially in embedded or when you're working with consoles on gaming or similar things, you want to have your software run on a new target. These days, we also have like PCs and laptops that are different targets. I'm thinking of Apple ARM CPUs and stuff like that. So when you switch to a new architecture, CPU architecture, or to a different operating system, when you switch between different embedded targets, there is a good chance that you will need to at least adopt a new compiler or switch the compiler, depending whether you want to switch or just add this as an additional target. Maybe you want to have access to something that is not directly a compiler, but is related to the compiler. You want to have access to some tool chains. You want to use maybe some build system, CMake or something like that, that currently does not support your current compiler, or other similar things. Or maybe you're changing a development machine. So we had a project where people were using Apple laptops, and they had to switch their machines. So they had to switch their compilers as well. The other way around, you don't want to go to something, but you want to get away from something, which can be a valid reason. You want to get away from a buggy compiler, a buggy tool chain, something like that. So anywhere but here. This can also be a reason to switch your compiler to get rid of the old one. So this one I had in the past with a project where we were using a relatively old compiler that turned out that under the hood it was from the late 90s, and we were still using it in 2015. And the compiler had internal compiler errors when we just would flip to header includes. On occasion, the debugger that came with the IDE with the compiler would crash after half an hour of debugging to a breakpoint, and then we had to start over again, and at some point we had just the pain and said, okay, we want to get rid of this. Well, just switch a compiler, right? 9 years ago, I had a talk about this old project, about this old compiler we wanted to get away from. That was mainly about clean code, but this one slide survived from that talk. It's not that easy, usually. So if you're going from GCC 14.1 to GCC 14.2, it's probably relatively easy. GCC 14 to 15, GCC to Clang, GCC to MSVC, it gets harder. So usually you need multiple steps. It is a process that you need to plan. It's not done in one day or in 1 week. And since it takes that time, you usually want to have both compilers running in parallel, because you can't just phone your customers and say, well, for the next half year, you won't get any updates from us because we are switching compilers. Usually doesn't go well. So you want to be able to fix bugs in the old code base. You want to be able to add new features using the old compiler, and at the same time work on making your project compatible to the new compiler. So for most intents and purposes, switching, at least from start, is more or less the same as adding a new compiler, because you want to have them to run them in parallel, right? If you say, I want to switch because I want to get rid of the old one, then you can plan accordingly. You say, well, in half a year, we throw out the old one so we can do some patches and fix them up later. But in most cases, it's adding and switching is the same. So the first thing to keep in mind is infrastructure setup. What do I mean with that? When you have a new compiler, you usually have a new development environment, because the compiler probably comes with a tool chain. Maybe you're switching because of the tool chain. So you have to set all of this up, right? You usually don't run your compiler like GCC -o something from the command line, but you use some CMake that you want to configure. Maybe you have a build system around it. Depending on what kind of tool chains you have, that can already be a roadblock. We've had a project in the past where we were using Yocto to build a full-scale Linux for embedded systems. And we said, well, C++11 is a bit outdated. We want to have a new compiler. So they said, well, for your new compiler, you need to have a new Yocto. But the board support package provided by the hardware vendor for this thing is written not really using actual Yocto, but something that happens to work with this years-old Yocto. And if you want to switch to a new one, you have to pay them $1 million to make a new board support package. Well, the decision was relatively quick. You have to think about licenses. Licenses for the software, for your compiler, for your toolchain, for whatever, for maybe hardware that you need to use with these. And these have implications, financial implications. Some compilers or compiler licenses can be costly. We've had a project where we said, well, this compiler is ages old. We want to have a new one to at least get C++ 14. And they said, well, this compiler costs $3,500 per person using it. So you better give us some good reasons to pay out 14,000 euros alone in licenses just for you to be able to use fancy C++ 14. Legal things can also be a thing. Depending on where you work or for whom you work, there can be people in legal in a non-software company who have a look at GNU, GCC. When we use this, we have to publish our source code. That is no-go. Well, no, you don't have to, but explain that to a legal person who says, well, I read the text, I know what's in there, right? Those are discussions that take some time. Political implications. In some companies, there's always politics involved, and if you want to do something new, if you want to invest time to do these things, to buy licenses, well, this is out of my pocket, out of someone else's pocket, and all these discussions. And you have to involve the IT department to actually purchase the licenses or someone else. And IT gets involved relatively quickly in some cases. How about the toolchain? Well, you have to find them, you have to install them, and you have to check that they work together. A build system, code formatters, for example, Clang format. Sometimes you have proprietary formatters. You have static analysis and code generators and whatever. If you're on a non-trivial project, then this list can get rather long. We've heard Anthony this morning, you want to have all kinds of checks, undefined behavior and static analysis, and your testing suite may need support by your toolchain as well. And switching these can also involve switching those parts of the toolchain. So you have your new development environment, and you want to install it on your dev machines. And there may be collisions with the old dev environment. We've had it that we installed a new version of a tool, and the tool was under the assumption there's only one installation of this tool on the machine, period. And they were not backward compatible. So you installed the new version, the old version was thrown out, and the project on the old compiler, on the old toolchain, wouldn't compile anymore. Or it would compile, but the formatter wouldn't work, or something similar. So you can consider having separate laptops. I've seen that. You can consider using VMs, Docker containers, WSL, different instances, whatever works. Great. We've hit the first main milestone. We can compile a bare-bone project on our machine because we installed all the things we need. Next step, CI environment. Because we don't only want to have it run on our machine, we want to have it run on a CI, right? Basically the same steps, +1 in difficulty in some cases because you don't have physical access to machines. If you have a compiler license that is bound to a USB dongle, then good luck, find the USB plug where you have to plug this in if your CI is in the cloud. Usually, CI is working on virtual machines, so you have your way to get access there. Often these things are controlled by IT departments. In some cases, you tell your IT department, well, I want to have that and that and that installed, and they say, okay, it's done. In other cases, they say, you want what, please? And then you say, well, I need this kind of hardware and this amount of memory, and then say, well, here's our list of our 2 Amazon instances, choose one. And it's not the one that you need. And then you tell them, well, if you don't have the instances we need, then let's just put an actual PC on someone's desk and plug it in. And the IT department goes, what? They won't allow this. Or some won't allow this. So make sure you contact them early and tell them what you're planning to actually get their okay and work out how this can work. Now that you've done your build environments, please document them. It's great for everybody who has to do the setup as well. If you have a larger team and everybody takes 2 days to figure out how to do this setup, and every setup is slightly different, and you get compilation differences between setups, it's a pain in the backside to actually analyze those. So good documentation is great. Having some setup scripts is better. What worked for me and the teams I worked with in the past quite well were Dockerized builds, because you can use those and just plug them into your CI infrastructure. You can plug them into your local machines. You can switch quickly, and they're separate from the old machine or from the old Docker container, so you can have them in parallel. But that's only one way. There are ways where you can't use Docker containers if you're building on Windows or something like that. So it is definitely something to figure out and to plan early. And having these documented and repeatable as a setup is great if you have, like, 2 years from now, someone tells you, well, we have a bug, and you figure out, well, this bug is back then in 2025 already, so in the old compiler. So we have to recreate that build to actually maybe debug it and stuff like that. Great, new milestone. Works on everyone's machine now. Let's talk about dependencies, because most of your projects probably just don't work in plain standard C++ and no external dependencies, right? Anyone using a UI library? 2 people, okay. Anyone using some other libraries? Couple of hands, okay. So, third-party libraries. You will have to check that those are compatible actually with the new compiler, that they support your new compiler, because not every library supports every compiler. You may have to rebuild them locally. You may have to set up a CI build if you build them from scratch, from source code. Or you have to buy licenses for closed source binaries for that different architecture, for the different compiler. You have to make them available to your team, so either distribute them using a USB stick or something like that, or rather set up something like a Nexus, some repository where everybody can pull them from. So this is additional work. If your library actually is not available for your new compiler, you need to find a replacement or drop the idea to use a new compiler. So, for example, if you switch operating systems and you're using actual system calls, Linux headers, and your new project is on Windows, you don't have the Linux headers there, then you want to probably use Windows.h or something similar. You want to replace them. You have specialized libraries. You want to find alternatives with preferably a similar design, similar architecture, because if your library dictates your architecture, or at least part of your architecture, and you switch to a library that has a different architecture, you suddenly have a whole bigger project because you have to change the whole architecture of your project, right? These quite often come with libraries that are GUI libraries like Qt, for example, which tells you, well, you have your Qt app and you have things built on top of this, and you have some wiggle room, but they tell you some things that they expect you to implement them. Sometimes you don't have alternatives, and then you have to decide, do we roll our own, or do we take what we have? Maybe you have an open source library that has been implemented for the earlier target, and yet now you have to implement it or changes adapted to the new target. Then, well, congratulations, maybe you just have to become a maintainer of a new library. And then, in the end, you have to decide if you keep the old compiler, do we have a full replacement for the old compiler and for the new compiler, or do we say, with this compiler we use that library, with that compiler we use the other library? It depends on the situation. I mean, the Linux, Windows stuff that you can't replace, well, but if you say, okay, this new compiler doesn't support our GUI library, then we just throw it out and use a new Go library for everything, it's possible. So in that case, you go to these steps with conditional compilations. Wherever you included your old Windows header, you now want to include your Linux headers, or the other way around. So you start introducing these if-defs in your code. And you probably don't want to make this in every single file that you have. So there is some refactoring to be done. And also, linking is the same. You want to link to the old library or to the new library, depending on what your current platform is, right? So this is how it could like in CMake code. Consider using project-specific defines. So who has been here earlier? Joel had like his defines where he had like these EVE underscore as a prefix. Consider using your own prefixes, because all the libraries that you use will use versions of this. And if you search for just underscore compiler MSVC or something like that, maybe your other libraries, third-party libraries, have already been using this, and it's not the same define that you would be using. So you have clashes of defines with the preprocessor, which is just a dumb word processor, which is really hard to debug if you have these clashes. And if you plan or envision that in the future you will have to switch compilers again or add compilers again, try using these. Have else branches that don't compile, where your compiler just throws an error. Because when you then come and say, well, now I have my third compiler, underscore I don't know what, then you run into these and you find all the places where you have to check what do I do in this case. If not, well, it just compiles. It's just this or else, and then you run into the else branch, and it may or may not be the one that you want to do with your new compiler. So, as I said earlier, you don't want to have these if, else, ifs everywhere. So what you want to do is encapsulate your dependencies. Have your CPP files that do the stuff that calls your Windows sources or the Linux system calls or your GUI libraries, and not have them spread out all over your code base. So you have specific locations where these compiler-specific things are located. So we have fewer points for conditional compilation and linking, and most importantly, your unit test in most cases can be written just against your business logic and don't have to care about is this Windows or is this Linux, because we don't want to have system calls in unit test anyway. And you have the separation of concerns, single responsibility, so separate things from each other that don't belong to each other. Doing that after the fact can take quite some time. We have had a project in the past where we wanted to get rid of that old compiler, and that old compiler had support for a Delphi GUI library, which we were using. And we had 130 GUI classes tied to that Delphi library, which contained roughly a third or a half of our business logic in the GUI classes. So you couldn't just throw them out and say, well, we use a new library now, the new GUI library now. So we started a project to prepare for the migration and said, well, now we separate our GUI classes into model, view, presenter. Model and presenter being pure C++, view being tied to the GUI classes, so in the end we would just have to throw out the views to get something different. 1 year later, we had done about 10% of that. I did the math and said, well, I'm off. I actually quit right after that because it was not maintainable. It was not the only reason why I quit, but it would have taken 10 years. I think they scrapped the project at some point and they stuck with the old compiler, got to a new version of the compiler, which is now Clang-based and maybe a bit less brittle, but it was a bit of a waste of time to actually try it. All right, we fixed our dependencies, or we know what dependencies to use in the future, so now we can port the project. Let's try to compile it. We call the compiler via our build system, so CMake or whatever you're using, meaning you have to integrate the new compiler into build scripts. You have to make CMake aware there is actually a different compiler, and there is maybe a CMake flag that switches between those two compilers that we have. You have to fix those command line options. You have to add your defines for conditional compilation to actually your compiler calls, so your CMake tells you, is this my project GCC or is this my project Clang or whatever. Warning flags, whatever is compiler specific, you have to adapt those in your build scripts, which is also will take some time. And then you hit compile. Does it compile? Most likely. Whoops, most likely not. And we are back. We had the dependencies, and we're compiling now. Okay. Let me fix this quickly. Right. So sometimes you're using compiler-specific extensions. They may be in your code base. For example, you want to always inline some functions that are performance sensitive. Attribute always inline is in GCC. Force inline is MSVC. Clang understands both. There are lots of cases like this. Non-standard extensions, compiler intrinsics that you will be calling. We've had in the current project, we had something where there were like byte swapping and things like that, where you're just calling a compiler intrinsic. And those won't compile with the new compiler. So what you usually do is you define your something force inline. And if it's MSVC, it's underscore force inline. If it's GCC, it's the attributes one. And you get multiple of these. And then you just write them, my force inline, calculate, and so on. They can have slightly different semantics. In 99% or 95% of the cases, it does what you want to do. But sometimes you get to things where you can get bugs that because of these slightly different semantics, and you have to figure those out, what to do there. And there may be cases where you have to actually rewrite a whole function for your new compiler. DLLs, the standard example of DLLs and import-exports. If you have a Windows compiler and you have an actual DLL, then depending on whether you are actually compiling the DLL, you have to define the things that you want to use elsewhere as DLL export. If you're defining the client that uses your DLL, you have to define those functions as DLL import. And on Linux, you don't care. You don't do this because you don't have a DLL, so you have shared objects. There are other things to hide symbols that you don't export on Linux and similar things. And there are CMake flags that you can use to generate these export DLL headers and stuff like that. But this is a very common example that people have these when writing DLLs. Compiling with a newer standard. So my first advice would be, when you switch to a new compiler, first, even if you want to get to that new compiler, to that new standard, compile with the old standard, because you already have enough on your hands to actually make it work. With the new standards, you have different things, especially C++ 17 introduced and deprecated and removed quite a few things. So these removed features you hopefully don't have in your C++ 11 and 14 code, like auto pointer and something like that. But still, it might be there. One thing to be pointed out, std unexpected has been removed with C++ 17. Std unexpected has been reintroduced with C++ 23. But std unexpected is not std unexpected. This one that has been removed is an exception that got thrown when, no, it's a handler that got called when you threw an exception that the exception specification did not mention. So before C++ 17, you didn't have no except or no except false. You explicitly could tell on your functions, this function throws that or that or that or that exception, and when another type was thrown, then unexpected got called. In 23, I think, it's with std expected, then unexpected is just the error case of this variant k type yes or no thing. So it's something completely different, but they have the same name. Let's get to implementation-defined behavior. The implementation-defined behavior, the standard says that some behavior is implementation-defined, meaning the compiler can define it, and the compiler has to document it. In the C++ 23 standard, there's a 4+ page index of what is implementation-defined in the standard. For example, include might find different files, because the way the preprocessor looks up what to actually include might find files different ways, because it can go through different symbolic links in a different order and stuff like that. So you have to be aware of this. Some things your code uses might not exist on the new compiler, because the standard for many things says, well, these are the 2 or 3 things that are in the standard, and every compiler is free to implement additional things. For example, for parallel algorithms, there are like 2 or 3 different things that can be made parallel, and the compiler may define more. Things that your code uses might have different types or sizes. Many return types of vector, begin, iterators, whatever, may be of different types. Something we came across recently is from a string view, the begin and end iterator. In one compiler, it was an actual iterator class that was a thin wrapper around a character pointer. In another compiler, it was just a character pointer. And we got a warning in that other compiler, I think it was GCC, because we dereferenced the iterator and then took the reference to actually get a character pointer. And GCC told us, you have a character pointer, you dereferences, and you take a reference to that element. Why? Because it already was a character pointer, and so we made nonsense to make it a character pointer again. That was just a warning, but still. Different sizes can be pointer sizes. You have systems where pointers are 32 bits, systems where pointers are 64 bits. So if your code depends on how large these things are, you may get into compile errors. Narrowing conversions, and all this kind of stuff. Then we have unspecified behavior. Whether names from the C compatibility headers are defined in the global namespace, where they belong according to the C++ standard, or in the std namespace is implementation defined, so it depends on your library. So apps versus std apps. So the C math header says there's a std apps. It doesn't say anything about apps. But usually your GCC says, well, that's just the same what our C header takes. So it just includes the C header and then says open standard namespace using : apps, using : this, and so on. So this is implementation defined, or unspecified, actually. Warnings. Your compilers have different sets of warnings. If you hopefully build with W errors, that can mean you have suddenly a lot of compile errors. Please get rid of those warnings, and not by ignoring them. Because turning those off is usually just a recipe to get those errors later because you have bugs in your code. If you're using static analysis way before you start this switching the compiler project, they will point out many of these things that will be questionable in new things. All right, so we got rid of all our compilation errors right now. So next milestone, it compiles. Does it run? Does it run correctly? We have this thing called undefined behavior, which we already heard in the keynote a bit about. Anything can happen. That's what we learned this morning. Quite often, code with undefined behavior just works. Or the other way around, if you have a sufficiently complex project and you're not using UB sanitizer and all the static analysis and so on, there's a very good chance that your project contains undefined behavior and it just works as you intended. If you switch to a different compiler, all bets are off. There's implementation-defined behavior, the runtime part. For example, what type info name returns, or what source location current returns, the exact formatting. Those are strings that you get. I would say it's mostly debug information. If you rely on those, maybe on your test or something like that, you probably get errors because they won't match what you expect on the new compiler. We had this especially with the source location current or similar things, like the __file __line and so on, formatting stuff. when you have like a log file and you have a relatively high-level test that just says, well, run this thing and then pass the log file, and the log file should be the same as what I had before, approval tests, this kind of thing. With a new compiler, these log files look different. And your comparison algorithm says, well, these log files are not the same, so there's a bug. And you just say, well, it is the same, but I have to account for these things. Don't buy logic on those. I have seen cases where people have written, if type info.name is this, then I have an integer and I know what to do. Please don't. There are implementation-defined types. This is a CAN package or something similar to a CAN package, so a network package that we send over wire to a different device that has an unsigned char, including some flags. It has an int16t for speed, and it has a long for the two longs for the positions it wants to move to. Can you spot the problem? Yes? Size of long is platform dependent. So we moved from a 32-bit system, the same code on a 64-bit system. It sent the thing, and the other side received the thing, and the motor moved something against the wall, because these 32-bit and these 32-bit in the original version were now 64-bit, and it just interpreted the first position as these two positions, and the values were way off. Next thing, old code base. Suffix delimiter was a minus minus, so we have some strings with a minus minus, maybe. And then we say, well, get the suffix of this name or whatever it is. We find the suffix delimiter, and if it's not found, then return an empty string. If it is found, then we just return that suffix. Problems? Well, name.finds returns a size t. An unsigned may or may not be as big as a size t. On a 32-bit system, size t and unsigned were 32 bits. On a 64-bit system, size t was 64-bit, position was 32-bit, so those never were equal. And our substring wrote through some exception, or it was not quite this code, we got an access violation because we tried to access something like a couple million into the string that doesn't exist. What we could do here is, well, to write this, I had to turn off clangd because clangd helpfully just gave me squiggles in C-line when I wrote this, when I tried to reconstruct this. You can use auto with newer C++, well, newer since C++ 11, and then we'll just do the right thing, right? Or you can write size t. You can also try to use curly brackets instead, and then you'll get an error because your unsigned that would be a narrowing conversion, and that doesn't compile, so there are all kinds of things. But if you have like an old code base, these are the things that you don't find by compiling. Those are the things that you find with a static analysis tool or at runtime when something crashes. This was a fun one. So we were writing an ARM device, code for an ARM device, and at some point we decided it is probably a good idea to test our code on our laptops as well. So just for test reasons, I wrote this function, print all ASCII characters. So anything just skip the first 31 or so that are unprintable and then just print the printables. Well, there's a bug in there because 127 is not a printable one, but that's a different story. Just put this character out. Works flawlessly in ARM. You get like, you boot your machine, you get like all these characters, and you say, okay, it's working. And then I started to run this on my Intel laptop. and somehow it didn't get to the breakpoint I had set much later. Well, car is not signed, or is signed or unsigned depending on your implementation, on the compiler. On the ARM compilers that I could find, it is unsigned, so 128 actually is a value that car can have. On Intel, it's signed, so 127 is the maximum. So this is always true, and the loop will go round and round and round. So you have int overflow, undefined behavior. You will try to put C non-printable characters, negative characters, whatever. I'm pretty sure there was some undefined behavior in that as well. So when I looked then at my terminal and I saw this thing running through and through and through and through, okay. I did some experiments with this. Let's count the printable ASCII characters. We have some function is printable that tells us yes or no. And here you already see I had clang D in this, and clang D says, well, this is always true, this less than comparison. Just count this. And then we have a main function, and we count our printable ASCIIs. Clang says, well, if I C is printable in the same translation unit, then I can figure out that is printable doesn't throw an exception, because if this were to throw an exception at 126, then this would not be undefined behavior, and the loop would return, right? But if is printable is visible, and Clang can figure out is printable does not throw an exception, then this is undefined behavior, and this whole function doesn't make sense. You can't even call it without invoking undefined behavior. So I just throw it away to make your executable smaller. And when you say, but I want to call this, then Clang says, well, let's see in the object in the object file, well, count printable, whatever is after that will be called. So if is printable is implemented after count printable, then I got this value. When is printable is implemented before count printable, and count printable is the last function in the object file, then that would be a segfault because you try to call a function that does not exist. And if is printable is implemented in a different translation unit, then Clang says, well, maybe it throws, so I just have to implement this, and you get the endless loop again. Welcome to undefined behavior. So how do we prevent surprises with implementation-defined, undefined behavior? Try to get as many warnings as you can before you switch. So crank up your warnings in your old compiler, add static analysis tools, add UB sanitizer, whatever you have. Fix those before you switch, because they will bite you sooner or later. So I already told some strategies, but overall, do your research first. See whether your compiler and toolchain are available for your new system, for your new target, for your new laptop, or whatever you're using, whatever reason it is why you are switching. Basically verify what you're going to do actually has a chance to work. Check with your IPT department, check with legal, check with procurement, whether they are willing to spend the money for the licenses, all these kind of things. Check your libraries, that they are available, that they have been maintained, because if you have a library that is available for GCC but has last been touched 8 years ago, then maybe be careful adapting it. And then try to have an overview which language extensions like these attribute or compiler intrinsics you're directly calling in your code, which can be hard. Then make a plan. Not just, yeah, next sprint we will switch a compiler. Make a roadmap. What do I have to do? When do I have time to do it? You will have to plan in feature development, bug fixing in between, because, well, sadly, we all have customers that will use our product actually. Not just, yeah, I'll install it on Thursday, I hit compile on Friday, and by Wednesday next week I have everything fixed. That won't work. So prepare your code base for the switch, maybe figure out where do I call all these library and system headers, and maybe reduce those instances to a few instances, like encapsulate everything away in a system wrapper or something like that. Can be feasible. Encapsulate them so you'd only have to fix those encapsulations and not everything in your code base. Fix your warnings. Refactor your build scripts. So you can beforehand say, well, if I have multiple compilers, where do I have to touch my build scripts? Because when your build script is doing something very GCC specific, because you have only been using GCC so far, then maybe you have to say, if I'm using GCC, then I do this, else blank for now, but we will have to fill this in later. Verify your infrastructure setup when you have done it, that you actually can compile things, document it, and then when you say, let's run things, start with the unit tests. Because the tendency is that your unit tests have the least dependencies to outside things, so you don't get hit with everything all at once, with your third library compatibilities and the third library that you chose is not actually behaving as you expected it to be. But you get all these undefined behavior, implementation-defined behavior things that we've seen earlier. And when you have fixed those, then you can actually go ahead and say, oh, well, what happens when I start my acceptance test, integration test, if I integrate this with these libraries that I've bought for this, and see how those libraries behave. And then work your way up from them to full integration to get this Swiss cheese that Anthony mentioned earlier to its full thickness. All right. That was a bit quicker than expected. Are there questions, comments? Thank you.
Hi, thanks for the talk. So you said that because switching compilers can be hard, maybe for some time we should try to use two compilers parallelly. And I think a lot of the talk focused on how to prepare for switching compilers. What do you think when somebody wants to use two compilers at once? Should you be having these if-else blocks all in your code base for the two compilers? I mean, it seems a bit messy to me.
I mean, if you are using two compilers, if you just say, okay, I switch this one compiler off, I take 3 months, and then I have the new compiler, then you don't have to have these if-elses, you just have to change your code, right? These if-elses are needed when you have your two compilers running in parallel or multiple compilers. And so yeah, when you are targeting multiple systems at the same time, you will have these in your code base. If you look at third-party libraries, open source libraries, they have these all over the place. And they usually have like their header where they do this compiler and platform detection and say, well, I'm on this detection, I'm on this platform. And then you just see inside the actual code if something lib Windows or if something lib Linux. And this is basically the way that I would say to adopt instead of having if __ Windows or something like that, to have this detection in one place and say, okay, these are the things I actually care about. Because sometimes you care about Windows or Linux, or sometimes you just care about Clang or GCC. And these can be orthogonal, right? You can have Clang on GCC on Linux, you can have Clang on Windows, GCC on Windows, GCC on Linux, and so you're actually having your defines tailored to what your needs are. You don't need all of those, but you need some of those depending on your situations. And you want to constrain these to as little code as possible so you don't have these if-else cascades all over your code base, because that's hard to maintain.
Have you ever tried to do that with modules?
No. I have been so far in projects that have existed for more than half a year or for more than a year. So these projects have not been using modules so far because, well, I still have to hear from projects that have successfully in the field on a larger scale have used modules. I know there are some smaller companies, there are some that are using modules successfully on one single compiler. But I don't know how far the adaptation of build systems is actually portable between compilers for modules and how far the adaptation has gone.
Talk for next decade.
Hopefully in 4 or 5 years, but yeah, it's not something that I expect to see in the next year or two. I would be pleasantly surprised, so.
Thank you for the talk.
Thank you.
I have a very specific question in this regard. Do you have perhaps any experience with dealing with non-contiguous memory regions when switching to GCC?
Dealing with non-contiguous memory regions, I've touched that briefly, but not when switching to GCC, no.
Okay, thank you.
You have problems in that area?
Yes.
Thank you, Arne. I have a couple of nitpicks, if you don't mind.
Sure.
One about the CMake slide. Please make use of generator expressions, which is modern
Yes,
CMake.
absolutely.
Which is like a ternary operator, basically.
This one's right?
No. A bit earlier. Yeah, that one.
That one, yeah.
Exactly, that one. One can express that directly
Yes.
within the usage of target sources and target link libraries. They are all generator expression enabled.
I have contrary opinions about that with myself. So when I am in a project where we have C++ developers and especially junior C++ developers who know C++ decently, haven't had that much experience with CMake just yet, then for most people this is more readable than generator expressions. I agree that generator expressions are the modern CMake way. I would say it's the same way that templates and so on are the modern C++ way. So there are some trade-offs between readability, between your target audience, and between something that becomes expert code at some point.
Yeah, the difficulty is this is actually a best practice. And so
I know.
Making a trade-off between best practice and readability, in my opinion, is always in favor of best practice. But we digress. The other thing would be, how do you deal with education? So compiler warnings and static analysis output is actually a kind of education. And most developers tend to be more akin to, or more open to being educated by a machine than by a human. Mm-hmm. So if the compiler says this is wrong, they accept it. If they get that in a code review by another developer, they don't. So if you now create a team of people who are responsible for fixing everything for everybody else, this vast developer base doesn't learn. So how do you distinguish between rolling out or forcing all these changes through an entire team of for the entire project so that they learn versus automating that in or grouping that in a very small team?
I wouldn't group that in a very small team. I would actually go ahead and say, well, we will have a rough patch ahead, maybe a rough week or so. We will turn compiler warnings and errors on, crank them to the maximum, and we will see what happens. Mm-hmm. And maybe we spend the next 3 or 4 days as the whole team, fixing these errors until everything compiles again. Or maybe we just go iteratively and say, well, turn on some warnings, turn on some more warnings, and make a learning session out of it. So if people get some warnings or some compiler hints that they are not sure about, that are new to them, have a talk in the developer round that we usually have in teams, where we sit together and say, well, there's not something new to learn here. Let's have a look at this, because this is something that you don't see every day. So this is why the compiler warns about it, and this is how we fix it.
One variant of that is using namespace boost and using namespace std in the same translation unit. I know you explicitly said this is not about switching the standard,
yes.
but usually with a compiler you also change the library and the available features in the library.
Yes.
And again, you would want developers to avoid using declarations.
Absolutely, yes.
So again, you only get them there if they themselves feel the pain. If they don't feel the pain, they will continue making these mistakes over and over again. So it's, in my opinion, very important to have the pain spread out over over everybody.
Yeah. So do this with the whole team. Don't say, well, I'm the expert, or we know the expert, and they will lock themselves into their office for 2 weeks, and then they come out and everything is shiny and new. That won't help. Absolutely. There's one more question over here.
Thanks for the talk.
Thank you.
All good advice. But maybe another thing I could add that worked for us is just if you're starting a new project or you're not too far into it, just use multiple compilers. Don't freeze your toolchain forever. Just upgrade whatever you have in standard Linux distribution. Use your programmers to find new warnings, errors as they upgrade their working PCs, basically.
Yeah.
And just don't over-engineer, write simple code that compiles with multiple compilers, that doesn't use or exercise differences in those compilers, if possible. If you don't have business value in that, just don't over-engineer.
Yeah, I agree. So if you have a new project, you do best to say, okay, we have our specific compiler, and maybe we just run it on GCC as well, or some compiler that is widely available, just to have this double check that we don't do anything fishy in the code base. Because, well, this was a cautionary tale. If you start a new project and you don't do this, then you get this later, right? All right. I think that's it, yes.
Thank you very much.
Thank you.